Hello and welcome again to my physics online video lecture series. Today's video we're going to be talking about the concepts of dimension and unit. This is part of our sort of introduction to physics. This lecture would go with a set of other lectures that corresponds to usually the first chapter in most introductory physics textbooks, be they a calculus-based text like the Giancoli or the Survey and Jewett or the Sears and Zemansky, or be it something that's more like the college physics textbook that's algebra-based. This is the Sears and Zemansky version, or OpenStack's college physics, or what have you. So this is meant to be a relatively short lecture, or really more like a short introduction to this topic. I intend to have a follow-up video in which we talk about other things such as dimensional analysis. The idea of today is that we're introducing dimension and unit, and these are both things of importance when we are talking about measurements. So what does each of those things mean? So dimension would be in some sense like the kind of thing that you're measuring, and then unit is the standard of measure to which a given measurement is compared. So what kinds of things can I measure? Well, for example, I could measure length. So length is a type of dimension. I could measure speed. Speed is a type of dimension. It's actually a complex kind of dimension that's made up of more basic dimensions. So length and time are generally taken to be sort of basic measurements. Speed is then a combination of these. That said, we also have units to go with each of those. And the units are basically the standard which you're using to measure something. So for dimension, we might be measuring a length or a volume, which is consists of essentially like three lengths in some sense, a speed, a time, a frequency, etc. The units are the standard of measurement that we compare these to. So if you're wanting to measure a length, you might say that this is so many inches, or so many feet, or so many miles, or so many meters, or so many centimeters. So that would be a unit. Your standard unit might be the meter. And so when you want to say how long is something, you're comparing it to that standard. So a meter is roughly the length of a meter stick. So if I say something is 5 meters long, in some sense I'm saying it is 5 times as long as a meter stick is. Volume, we might use cubic meters, or we might use liters, which is a liter is 1,000 cubic centimeters, and therefore is 1/1000th of a cubic meter. We could also use a fluid ounce, or a quart, or a gallon. Quart is roughly the size of, just a little bit smaller than, a liter, for what it's worth. Speed, you might use the unit of miles per hour. You might use the unit of meters per second. So you can see here directly, like this is combining meters and seconds. Time, you could use the second, usually just abbreviated with an S. Meter is usually abbreviated with an M, so meter, second, etc. Okay, so that is what dimensions are and what units are. In some sense, we could end here, having kind of explained the two concepts, but I wanted to go just a little more in depth about these things because there are different systems of units, and there's different sort of methods for determining what the base units, the base dimensions are. So for physics and for science in general, we use the System International SI units, particularly the MKS base. Sometimes we use CGS base instead. So what do these two things mean? Well, MKS stands for meter, kilogram, and second. And for what it's worth, CGS stands for centimeter, that's the C, gram, that's the G, and then second. Both of them actually use the second as the time unit. The meter is the length unit for this one. The centimeter is the length unit for this one. Kilogram or gram represents different values of mass. Okay, so these are different systems for the System International. There's also imperial systems. So imperial systems are kind of customary systems. These use a different set of units. For example, we could have feet, slugs if you want mass, and seconds. The second is basically the same whether you're using US customary, British customary, CGS, MKS. You could use pounds instead of newtons for force, for weight, among other things. Now, because of the fact that we're doing here physics, we're mostly going to be focused on this meters, kilogram, seconds system base within SI. So it might be worth asking, where do these three things come from? Where do we get meters and seconds and kilograms from? Originally, or traditionally, this was used the standard meter, and so this was a bar of iridium platinum alloy, which was defined to have a length of 1 meter. Iridium platinum tends not to degrade over time, especially if it's kept in vacuum, so the length remained more or less constant. It's kept, I think, at room temperature under vacuum and so on. In 2019, there was a revision to the SI units. I think it's the 9th revision, in which this meter was redefined in terms of the speed of light in vacuum, the exact value of which I'm showing here. This is an exact value, by the way. There's infinitely many zeros after this 8. And then the hyperfine frequency of a cesium atom, which I will define when we talk about time. So basically you could say in some sense that in 1 second, which is how this hyperfine frequency comes into play, in 1 second light travels basically this many meters. Okay, and so 1 meter is 1 over this many of the length of space traveled by light in vacuum in 1 second. Does that revision mean that we've really changed how long a meter is? Well, yes and no. It essentially means that instead of saying that the meter has this exact value given by this artifact, this bar of metal, the meter now has an exact value, but it's not defined by any tangible object that you hold in your hand. It's defined by light. Does that mean that all your meter sticks are now inaccurate if they were made before 2019? No, not really. The difference is so minuscule that the precision of a meter stick doesn't capture it. So a meter stick is still a meter stick to plenty of precision, to within the limits of precision that it already had. All right, that's your meter. What about a second? Let's do a kilogram first. We'll do a second last. Traditionally, we used a block, a cylindrical shaped block of iridium platinum alloy, and said this thing has a mass of exactly 1 kilogram, and so you're comparing to the mass of this thing. It's been redefined a few times. We could redefine using Avogadro's number. Basically, we could say so many kilograms are equal to so many moles of carbon, for example. So if you've taken chemistry, you're familiar with molar mass. So we would essentially say how much carbon do you need to have, how many moles of carbon do you have to have in order to have 1 kilogram. It has also been redefined in terms of another fundamental constant, the Planck's constant. So with Planck's constant, the definition basically holds that this right here is the exact value of Planck's constant. The joule in turn is defined as 1 kilogram times a meter per second squared. So since we've already defined what a meter is, as long as we can define what a second is, and as long as we say this is the fixed value of Planck's constant, then we now have a definition for the kilogram as well. And again, these changes do not mean that there's a noticeable difference in how much is a kilogram. They're on a very, very fine precision. Okay, sort of last one, I guess, for this particular set of 3 that I'm giving definitions for, and then I will talk briefly about what are the base units. The second was essentially defined at one point as 1/3600th of an hour, where an hour is a 24th of a day, where a day is how long it takes for the Earth to complete a full rotation. It could also be defined in terms of years, so how long does the Earth take to go around the Sun? It's been redefined in part because both those numbers actually fluctuate. Now we can define the second in terms of the hyperfine frequency of a cesium-133 atom. So this frequency sort of defines the second. This is how many periods of this hyperfine transition would occur in each second. And so now you can go and use that combined with, let's say, the speed of light to define for us how far is a meter. And you can now use those two combined with the Planck constant to define for us what is a kilogram. Alright, so with the 2019 revision, there's 7 fundamental constants, of which I've got 6 listed here, that are defined to have set values, and then our base units are defined in terms of those constants. The one that's missing, and which I'll show on the next slide anyway, is the luminous intensity. So your luminous intensity is defined down here. We're not really going to use that much in introductory physics. The rest of the base quantities from which all the other quantities can be derived are listed here along with their definitions. And that's all for today. Thanks for watching.